Now let us look at the component of time series. The traditional approach to time series analysis focus on decomposition, where the total variation in the series is broken down into 4 distinct parts: trend, seasonal, variation, cyclical changes, and irregular fluctuations. This decomposition helps us better understand the structure of the series and prepare it for further analysis. Let us focus on the trend component. A trend represents an evolutionary movement in the data, either upward or downward in the value of the variable. This component is observed when a series shows steady growth or decline across several consecutive periods after accounting for the other components. In simple terms, it can be thought of as a long-term changes in the average level of the series. One change in identifying a trend is determining exactly what counts as long-term, since this can vary depending on the context and the series being analyzed. To illustrate the trend component, consider climatic variables which can exhibit cyclic variation over very long periods such as 50 years. If we only have 20 years of data, this long-term oscillation may appear as a trend. However, with several hundred years of data, the true long-term cycle variation becomes visible. Despite this, in the short term, it is thus often more practical to interpret such long-term oscillations as a trend, since it helps us understand the general direction of the series over the period we are analyzing. This graph gives us a long-term view of the data. That the blue line represents the full 200 years datasets, while the red segment highlights the 20-year snapshot we looked at earlier. At first glance, the red segment appears to show a steady upward trend, but when we consider the full 200 years, we see that this rise is actually part of a 50-year cyclic pattern, much like a sine wave. This example shows why it is important to look at the bigger picture. What seems like a trend over a short period may really be part of a long-term cycle. In short-term analysis, we often treat such segment as a trend, but keeping the long-term context in the mind helps us avoid misinterpretation of the data. The seasonal component, sometimes that's called periodicity, is a pattern that repeats regularly over a fixed period, usually within a year. For example, retail sales often spike during the holiday season, or electricity usage rise in the summer due to air conditioning. These are classic example of seasonal effects. The seasonal components can appear in series measured weekly, monthly, or quarterly. The key is we see similar patterns at specific times of the year, like winter heating trends or summer tourism peaks. Notice that seasonal fluctuations are regular and predictable, but unlike long-term trends, they have a period of less than 1 year. Understanding these components helps us separate short-term predictable variation from overall trend. Understanding this component helps us separate short-term predictable variation from overall trends or randomness in the data. This graph illustrates how seasonal variation affects economic costs over the year. The red line shows the price index for a particular set of goods over a 3-year period, and you can see a clear repeating pattern each year. Notice how price rise and fallen constantly at certain months. They peak in winter and drop in the summer. This is typically for fruits and vegetables, which become more expensive when they are out of season and cheaper during harvest periods. Seasonal components like these are not random. They reflect predictable, recurring fluctuations tied to natural cycles, production schedules, and customer demand based. Recognizing these patterns is essential because it allows business and policymakers to anticipate cost change and make better planning decisions. In short, this example highlights how the seasonal component can directly impact real-world economic factors, showing the practical importance of separating seasonal effects from long-term trend or irregular variation in a time series. Beyond seasonal effects, many time series display cyclic variation, which occur at regular intervals but is longer than 1 year. These cycles often arise thus due to broader physical, economic, or social factors, unlike seasonal patterns. Cyclic fluctuations are not tied to the calendar. Some oscillation may not have a fixed period but can still be somewhat predictable based on underlying influences. A cyclic example comes from economic data. We call it that business cycles. That periods of expansion and contraction can range from about 3 to 10 years, depending on the variable studied. But it is important to note that the existence and symmetry of such cycles are sometimes debated among the economists. Recent research even suggests that these cycles are often asymmetric, meaning that the growth and decline phases do not mirror each other perfectly. Understanding the cyclic components helps us separate medium to long-term variation from short-term seasonal effects and randomness, giving thus giving a clearer picture of dynamics in the system we are analyzing. Building on the concept of cyclic variation, this slide provides a visual example of how cyclical components appear in time series analysis. The graph shows the movement of an economic indicator, such as GDP, grows over time, measured as deviation from long-term trend rather than focusing on overall growth. It highlights the upward and downward swings that occur around this trend. Periods where the curve lies above zero line represent economic expansion, indicating strong economic performance. In contrast, when the curve fallen thus below thus zero, it reflects periods of recession where economic activity slowly down. One important feature illustrated here is that the symmetry of this These cycles, one important feature illustrated here is the asymmetry of these cycles. The duration and intensities of expansion and recession are not identical. Some downturns and sharper, more pronounced, while expansions may be more gradual or prolonged. This visual representation reinforces the idea that cyclic dash patterns occur over the medium term intervals, typically lasting several years and are influenced by broader economic forces rather than fixed seasonal factors. By observing these fluctuations graphically, we gain a clearer understanding of how cyclic behavior shapes real-world time series data. The irregular component refers to the unpredictable variation that remain after the main components of a time series, like trend, seasonal, and cyclical, that have been accounted for in time series analysis. These fluctuations are often described as irregular because they do not follow a specific pattern or consistent behavior over time. They may arise from unexpected events such as natural disasters, sudden economic shocks, or other random influences. It is important to note that irregular fluctuations are not always purely random. In some cases, they may include one-time effect or unusual occurrence that cannot be easily explained by the other component. Understanding the irregular component is essential because it helps us analysts recognize the limitation of forecasting and highlights the presence of uncertainty within real-world data. By separating out the irregular variation, you can better focus on underlying pattern and structure of the time series. This slide compares the predicted paths with the actual observed data in time series analysis. The blue line represents the predicted path, which is constructed by combining the main component of a time series, like trend, seasonal, and cyclical patterns. It shows the expected behavior of the data over time based on this structured component. The gray line, on the other hand, represents the actual observed data, while it is generally follows the same overall direction as the predicted path. It does not match perfectly. The differences between the two lines highlight the presence of irregular fluctuations. These are unexpected variation or shocks that cannot be captured by the model, such as sudden economic changes or random external events. This comparison illustrates an important concept. Although time series models can explain a large portion of the data, they cannot fully eliminate uncertainty. Irregular components will always cause some deviation between predicted and actual values. Understanding this gap helps us interpret forecasts more realistically and reminds us that all models have limitation when applied to real-world data. That concludes this part of the chapter 1. We have covered time series components. Thank you and see you